Hi, so am I audible? Hi, so let us start them. Um, uh, can someone please confirm whether I'm audible or not? Anybody?
Yes, there are.
Yeah, okay, cool, cool. So, hello everyone. Today we are going to have a few demos on some sketching algorithms that were discussed in the lecture. So, who should start first? Anybody who wants to go? Show me, maybe you or
Yes, sir.
okay, cool. So I have started the recording. So please go ahead.
I'm present the screen, so just let me know.
Yes, it is visible.
So good evening, everyone. So we'll be, as it was posted on the forum, that we'll be discussing on some of the algorithms on counting. One of them being Bloom filters. So let us just recollect Bloom filters before going into the demo. So a Bloom filter, as we have already seen in the lectures, that it's a space efficient data structure which is used to test whether an element is a member of a set or not. So, given a book's name, if you're providing a book's name, you want to know whether it is present in the library or not. So that kind of a use case. I mean, you want to really know it fast whether the book is present in the library or not. So that's why we need an efficient data structure. So Bloom filter comes in use for those purposes. So we have also seen that false positive matches in this case are possible, which means that if an element is not present, it can be told as present, but there are very less possible cases of false positive matches. But false negatives are not possible. Deletion of elements is not possible in the vanilla Bloom filter algorithm. However, this deletion can be addressed with the counting Bloom filter variant, where for each bit we can keep a certain counter for addressing this deletion problem. But however, in that case, the false negatives do come into picture, but that is also in less number. And also, more the items we add in the filter, the probability of false positives also increases. Because the bits which gets occupied in the Bloom filter becomes more, and that's why if any query comes which gets hashed to any of the bits in that Bloom filter, I mean, the query, if it's not present, it gets hashed, then that increases the probability of false positive. Now, there are three operations essentially for Bloom filters. One is initialize, second is insert, and third is lookup. So under the initialization of Bloom filter, so let us say we have this Bloom filter, which is like 19 bits. So all of the bits are set to zeros initially. Then let's say we have got a string John Doe and also the Jane Doe. So there are two strings. And now we have one hash function. And using this hash function, we want it to get assigned. I mean, we want one bit to get turned on using these two strings. So this hash function gives a certain value, and we want the value to lie in the range of the size of the bit array. So we do a modulo operation with the size of the bit array, which gives us a value between 0 to the 0 to 80. So that's like lying between within the size of the bit array, which is 90. So let's say with these two strings, these two bits, the 6th bit and the 15th bit, gets turned on. So this is like the insertion operation. Then when we are, let's say, looking up for the string John, and we use that hash function, and it gets assigned, I mean, the value comes to this 10th bit, which is not turned on, or which is not given a value of 1. So it will be saying that the string John is not present in the Bloom filter. However, let us say we are looking up for these two words, James Bond and Jane Doe. Now, using this hash function, and let's say it gets assigned to the 6th bit, and the Jane Doe gets assigned to the bit which we initially found it to be here. But however, James Bond didn't insert it initially, but it got assigned to the same bit which John Doe had been inserted in. So it will say that James Bond is present, but however, that is not true. So it will lead to a false positive. So going ahead with these, this brief idea over the recapitulation of the Bloom filter. So now we are saying that we are going to use some hash function. So currently in this demo, I've used former hash, which is a hash function which can be used for the non-cryptographic hash function. It can be used for hash-based lookup. So for this hash function, there is a Python wrapper which is present, which is called MMH3. So we are using this MMH3 as, for generating the hash value for given any string. So basically we need to install this MMH3, and bit array also we install, but we can use normal Python lists also for this purpose. But bit array is it's nothing very fancy. It's a simple list where given the size, all the bits in that list gets initialized to 0, and whenever you want to set a bit on, you just mention the index and you can set it on. So now just to show that what MMH3 does. So this MMH3, you can use the function hash. You can call the function hash. Give an item or a string which you want. Let's say the scalable is the word, and you set a C. So every time you run this cell, you will basically getting this value. So it is basically giving you a unique identifier for this particular word. So this is getting hashed to some value. So this is a particular value which it is getting hashed to. So we will be using this MMH3 for hashing the inputs we'll be using in the code further. So we import these libraries, a math for finding the logarithm, MMH3 for the hashing, and bit array API using for initializing the Bloom filter. Now this is the class Bloom filter. So as I was mentioning, for the initialization, we are keeping this init function. So here the two main things are items count. So how many items do you want to insert in the Bloom filter? And what is the false positive probability with which you want to allow? So I really don't want my false positive probability to go higher than this. So that is the probability you can mention. So these two are the main user inputs which can be given. And so we initialize this with like f prop to this false positive probability. And then this size is the size of the bit array. Hash count is the number of hash functions we can use. So we have also in the lecture, it has been taught that we can actually find the optimal number of hash functions and the optimal size of the bit array. We can find given the we basically use those formulae in these two functions, get size for the size of the bit array, get hash count for the number of hash functions to be used. So we will go into these two functions, but these two functions will be basically giving us the size of the bit array and the number of hash functions, the optimal number. And this is the bit array, which is basically calling the library bit array with the size we get from this function. And as I was mentioning, we set all the bits to 0 initially. Now we come to the insert function. So there were there were three things: initialize, insert, and lookup. So we are now looking into the insert function. So before going into that, let us just check what is get size and get hash count. So get size is nothing but, we have, if you go through the lecture, you'll see. So this is like, the formulae is mentioned here. So it is like the number of items you have into natural logarithm of the false positive probability divided by natural log of 2 square. So this gives us the size of the bit array. I'm not going to the derivation. It is already mentioned. It is taught in the lecture slide. So we'll just go through the implementation here. And the hash count is so the number of hash functions we want. So that is nothing but the bit size array, which is m by number of elements we want to insert in the filter into log of 2. So again, I'm not going to the derivation. So we get the number of hash functions we want to use and the number of the bit size array we will get. So these two are returning us this size and hash count values. So now coming into the insert function. So this insert function, as we saw before, what it will do is for each hash function and within that each hash function, for every string we have, which is the item here, it will be basically hashing it to one of the bits in the bit array. So that is why we traverse over the loop of size hash count, which is like number of hash functions. We use MMH3 library to hash the item which we pass here, and we mention the seed also as I, which will be differing with the number of hash functions. And then we do a mod size, which is as we saw before, it is to just range the hash. It is to range the value from 0 to cell.size -1. So as we saw there that we have 19-bit array. So we have to get a value from 0 to 18. So that is the whole purpose of the modulo operation. So we get this hash v and then we append it to a list hash l. And what we do is that we have this bit array where we have set all the bits to 0. We just set that particular hash v to true. So that gets turned on. Now we go into the lookup function. What lookup function will do is that it will be, again, I want to see whether this item is present in my filter or not. It exists or not. So again, we traverse over all the hash functions. We get the hash value for that particular item, and we check whether the bit array with that particular index, any of them is false. So as we have seen in the lectures also, it's an AND operation. If either of the bits tells or is marked as false, it will actually return false. So otherwise, it will, if all the bits which are coming out of this, all the hash functions are true, then it will return true. So if any of the bits is false, it will be saying that it is not present in the filter. So it's an AND operation. So this is the lookup module. So now let's say we go into the part where we are inserting elements and we want to check whether it is present or not. So let's say we are inserting 10 elements, so n equal to 10, and we do not want a false positive probability of higher than 5%. So that is why we set it as p equal to 0.05. Now Bloom filter class, as I was telling you before, we basically need these two things: number of items to be inserted and false positive probability. So we call this Bloom filter class with this n and p, which is number of items and false positive probability. We get the object bloomf. So now when we are calling bloomf.hash underscore count, which is nothing but this particular variable, we will automatically get the optimal number of hash functions, because it is calling the function from, here itself inside this init, which is a type of a constructor in Python. So now when we are calling bloomf.hashcount, it will actually return the optimal number of hash functions given the total number of items we are adding and the false positive probability. So let's say these are the words present. So we are adding these 10 words, and these are the words absent, like we are not adding words. So there are many words which we are not adding. So for each item in this list of present words, we are calling the insert function. So it is inserting in the Bloom filter all these words which you are seeing here under word present. Then, shuffle, you may do, you may not do shuffle, but I'm just calling some random import shuffle, just shuffling the word present list and the word absent list, because we are creating a test words here, which is like I'm taking from word present first 5 words and the entire list of word absent. Then again, I'm just shuffle is not very important here, just added here, just a test. So nothing much important. So test words, I am taking 5 words from word present and from word absent, the entire list. So now if we just print the inserted words, we can check that the inserted words are these. So after the shuffling part, I have printed this so that we can be sure that what are the test words. So because, so the first 5 words of the word present will go into test words. So now we are calling, so now here comes the task of the lookup. So for word in the text words, we are using that object with which we have the Bloom filter class object. So then we are calling the lookup function with the word, with each word in the text words. So if it is in word absent, so then it is a false positive, else it is probably present. So if it is in word absent, that means it was not inserted in the Bloom filter. So that is why it is a false positive. So if it is returning them, else bloomf.lookup word will come into this portion only when it will return it to be true. So if it returns true, then we are checking that if this word is in word absent, the words which we have not added in the Bloom filter, then it is a false positive. That means the word is not present, but it is being told that it is present. So it is a false positive. And else it is probably present. That means it's definitely present. It is not being told in Bloom filter. There is always a probability added here. So it is probably present. Else, if it is not present, so it is definitely not present. So these are the inserted words which were present, from the words present. Now we are checking for each of the words in this word, in these test words. So now we'll see that this word, let's say brusque, since brusque was not here in this word present, so it is definitely not present. And if we check for the word, present, so this present, you will see this is in the first 5 words. So that is why it will be telling that it is probably present. So you can actually, I don't have a false positive thing here, but we can modify the example such that you also get this false positive statement for some word. But I guess you can understand this part, that when we are saying it is definitely not present and when it is probably present, and the 3 modules which are important for the Bloom filter part. So if you all have any questions, you can tell clarify.
Okay, so if anybody has any questions, we'll wait for a minute or so. Please speak up if you want.
Uh,
So for those of you who joined a bit later, we are recording this session and this will be uploaded to the YouTube channel. So please don't worry, you will be able to view this later and catch up if you have any missed parts.
so I guess there are more questions, so we can go to the second part.
Okay, sure. Thanks, Shoman. So, Shrutima, do you want to try sharing the screen and stuff?
Yeah, sure. Am I audible?
Yes, you are audible. Yes.
Hello, everyone. So in this notebook, we will see an implementation of the count means scarce algorithm. So this count means scarce algorithm is applied for streaming data. So suppose you have n types of items. So for convenience, let's say you have some balls numbered from 1 to say 10. And now you're given a stream of data. So you have say balls 1, 2, 3, 4, 5, 1, 2, 3, 1, 2, and so on. So your task is to compute or count how many times each item occurs. So for that, in that scenario, we use this count means scarce algorithm. For that, we create a data structure, and then once we query the data structure, we can get an approximate count of the number of times an item is. So here we create, suppose we take say 1000 items. So we have balls of type 1000 types of balls numbered from say 0 to 999. And suppose we have a data stream of say 10 to 5 elements. So what we do is since we cannot replicate a stream, I'm just creating a random an array of size 10 to 5, where each value is within this within 0 to 999. So we can get the exact counts of how many times each of these elements appear in the stream by using the numpy unit function and setting this return counts argument to the true. So in this case, you can see that for the 1000 items that we have, and for the given stream length of 10 to 5, some of the counts are like this. So the counts of the first 10 items are like this. So 0 occurs 102 times, 1 occurs 96 times, and so on. So now, if the number of items is very large, we cannot go on counting each item individually. So in that case, we want to make this counting system more efficient. So we use this data structure called the count scarce data structure. It is basically a 2D array where there are say W rows and T columns. So what is W? So this count scarce data structure is constructed using certain hash functions. So W is the number of hash functions executed. So in that count scarce data structure, each row will correspond to one hash function. So since we will be using W hash functions, we have the W rows. and the number of columns D, the number of buckets these hash function will map into. So suppose we have some entry, say X, and if we do hi of X, it will go to the ith row and one of the D buckets in that ith. So in the lectures, it has been mentioned how to select this W and D parameters, the size of the count space data structure. So if we want some guarantees that we want our count to be within, say, epsilon error points, say we want 20% of error, and we want some confidence that if we have, say, 99%, we can say that with 99% confidence, we will have some, say, 2% of error. So in that case, we select the number of hash functions to be log of 1 by delta, where delta is the confidence parameter, and we select the number of buckets or number of columns to be 2 over epsilon. So suppose, for example, we take 8 hash functions and say each hash function maps to 128 buckets, then we can say with 99.6% confidence that we'll have an error of at most 1.6%, at least 1.6%. So for this example that we have taken, where we have 1000 types of data and data stream of 10 to the power 5 length. So for this example, I have taken 32 hash functions, and I am taking the number of columns to be 512. So now I create this count sketch data structure by initializing it to all zeros. So as you can see, I have created a W plus the matrix or W plus the 2D array and initialize it to all zeros. Now the next thing is how to construct this hash function. So for that reason, I have used the hash function available with Python. So you can suppose we have out of W, suppose we have some, say I want to get the hash value of the fifth hash function. So then it will come to this, it will call this hash function I. So instead of I, we will have 5. So we will do a random seeding using this 5 vector seed and use this get rand bits to get the 7-bit random number. So once we get this random and we store this random number at this variable, say mask. So suppose we have our entry, say we were seeing the 105th item, where X is 105 and mask is say 120. Because it is 7 bit, it can have almost one value 128. So here X is say 105 and mask is 108. Sorry, 120. And for I, suppose we are looking for a fifth hash function. So we convert this item X to a string and this item and this index I to a string. Then apply the hash function and do an XOR with the mask value that we got from this rand bits got. And then we return this hashed value. So since we'll be having W hash function, so for our case W is 32. So we'll create an array of functions where which will be stored in this hash functions array. Now, once we have this count sketch data structure, we have two tasks. Once we get a new element, we must update the count of that element in the count sketch data structure. Or if we want to know the count of an element, we want to query an element and we want to know its count, we have to query the data structure. So for this add count operation, I have written this add count function. So for simplicity, I am saying that for in the stream of data, each item has a count of only 1. So it can be, because as I mentioned above, for each entry you can have more than 1 count. So suppose call 100 is seen 25 times, so we have 100 comma 25. So in that case, for this C is equal to 20, C will be equal to 25. But for simplicity, we are assuming that each item is seen at once. So once we get an item, we'll check to see if it is in the string. And then for each of the hash functions, we will update the count. So for updating the count in the count gets data structure, we'll go to the ith row, then we'll retrieve the ith hash function, then we'll apply that hash function to the element x, and we'll enter it at the column modulo t, because there are t columns, we'll have to enter it at the modulo t. This value modulo t column. And whatever count was there before in that cell, we just update the price. So once we have finished computing this count step data structure, we suppose we want to query the data structure. How will you do that? So for querying, it is simple. You just have to go to that cell. So the cell number. So given an item X, you can get which cell it is mapped to by querying the ith row and this hash function ix modulo th column as we have done before. And since there are I hash function, you will get I counts, or each hash function will get one count, and you will have to take the minimum of that. This is because each item will be mapped to a cell, and the count of that cell will be at least the number of times items will be seen. It cannot be less than that, because if other items may be mapped into that cell, but it cannot be that less number of times. I mean that cell has been updated less number of times. So that is why we want to take the mean of that entries. So hence we name this algorithm the count mean sketch. So for this example, we had the stream of 10 to the power 5 elements. So I added each element to the count scale data structure. This is the array that I got. And then I tried to query each element. So I randomly over all the 1000 entries and got the count of each of those elements. So suppose now I want to check our value for or my count for item number 10. So this query will get me the count from the count scale data structure, and this KCP counts is the actual number of times that item 10 was seen. So here I printed them. So as you can see, for this case, we have a very good estimate because we're getting exactly the same same count as before. And then to evaluate the quality of a data structure, I have just taken the average count, which is 0.588. Now the things that can be altered here are these p value. So if we go and change this, say if we make this p value to be less, so then in that case our error will be higher because more number of elements will be mapped to a less number of buckets. That is, there will be a lot of collision. That is, the number of or the count will increase. So you can just play around with these different values of d and w to see how the quality of your count scales data structure is. So that's it. Any questions?
Okay, so let's wait a minute or two for some questions, if any.
still no more questions.
Okay. So again, for anybody who joined later, the recording of this video is going to be uploaded to the YouTube channel, and also we will be sharing all of these Python notebooks. So you have access to the code, you can play around with it like Shrutima said, and you can try with the various hyperparameters and so on. So the next demo will be presented by me, and we are going to discuss the FM algorithm. The FM algorithm is the Flajolet-Martin algorithm. So could someone please confirm that the screen is visible just once?
Yes, sir.
Okay, thank you very much. Cool. So to recap the setting, we are going to approximate the number of distinct elements in any given input stream of values. So this has a lot of applications. So here I am just referring to the course slides that are being discussed in the lectures. And there are a bunch of applications where this finds use, such as in internet routing algorithms or in various sort of analytics and so on. So the problem with the naive techniques is that the space requirement is terribly high, because let's say you have this universe of items and you don't actually know, let's say it has a very high number of distinct values, and the stream consists of multiple occurrences of some of those elements, and you need a lot of space to store each of the distinct occurrences, and we want to count the number of distinct occurrences under two criteria. One is that the algorithm should be making only a single pass on the input stream of elements. So given the input stream, it should look at every element only once and not more than that. And secondly, we should use as less space as possible. And fortunately, Flajolet-Martin, the FM sketch, satisfies both these constraints. So under the brute force setup, calculating the number of distinct items is a rather easy affair, because you just need to, let's say, have a set-like data structure where each additional element increases the size of the set by 1. And then at the end of the stream, you just calculate the length of the set, and that's all. Right. But again, that requires a significant amount of space. And so the question is, how can you do better? And it is possible to do better if you allow for some error to creep in. So if you do not want the exact distinct count, but you want an approximate distinct count within some margin of error, and you want the error to be as low as possible with as high probability as possible. So just to recap what was discussed in class, you have this function called 0, which we will be implementing in the Python notebook now. We'll be having a demo. So the 0 basically tells you the location of the rightmost one, or the rightmost bit which has been set. So here, for example, the zeros function, given this input bit representation, it returns 1. And here it returns 3. So as you can see, we are starting from 0 indexing, and 0, 1, 2, 3. The third rightmost bit is the first occurrence of 1. So given this zeros function, the sketching algorithm is quite simple. You start out with a hash function which maps any of the given input elements to a L-dimensional bit vector. So here L is a hyperparameter, and that dictates the target space of the possible bit representations, bit vector representations. So given L bits, you have 2 to the power L possible representations, and the hash function randomly maps each of the input elements to one of those L-dimensional bit representations. So once you have such a random hash function, you maintain a counter called Z or Z, right? So for each of the input elements in the stream, you first use the zeros function to get the rightmost occurrence of the one or the set bit. And then you have an integer value basically, which is the output of the zeros function. You have an integer value denoting the position, and that value is compared to the current Z. And if the value is greater, then Z is updated accordingly. So Z basically keeps track of the largest position for the set bit across all the inputs. And then the final estimate of the distinct count is just this value, which is 2 to the power Z plus 1 by 2. So it's a fairly simple thing to implement. And we had discussed example in the lecture. So let us now go ahead and look at the demo. So in this, we will be using very basic Python libraries, math and random and some statistics, which helps you to compute mean and median. That's all. And matplotlib, of course, for plotting. So like we discussed, we have to decide the size of the bit representation, the hash function output. And that for this demo, we have set it to 64 bits. So you have 2 to the power 64 possible representations for each of the input elements. And you can, of course, change it to smaller or larger values and see how the algorithm is affected. Now, let us at any time operate on an input stream of size 2000 for this demo. So basically, by definition, the input stream is infinite. It's an ongoing process. But for counting the number of distinct elements, the input has to be some subset of that input stream. And that size of the subset has been decided to be 2000. That's it. So we have a few helper functions which will be needed later on. So, okay, so this function is actually not needed. It's just there because, so this is a useful Python API just to quickly get the bit representation of any number in case you want to visualize that. So the more important function is this get rightmost set bit, which is basically what the zeros function does. And if so, first of all, let us take care of the edge case. So in case you have the input as 0, which means that all the bit representations are 0, then you do not have a rightmost 1 anywhere. And so we will just return the value of capital N, which is the maximum possible position of 1. So this is the edge case. And apart from that, for any other input integer, we have this line of code which gets us the position of the rightmost set bit. The logic behind the code is to just use the bit representation of the number. So let's say the input n to the function is 56. The bit representation, if you use the get binary function described here, the bit representation comes out to be this. And this minus of n basically uses the 2's complement of this number. And the 2's complement, you can see that the rightmost part of by nature of the 2's complement, the rightmost part of the bit representation following the rightmost one is the same. So in case you have forgotten about what 2's complement is, or you need a quick refresher, I have pasted this link here. You can quickly go through it. So now, given these two representations, if you just do an AND, then this position of the rightmost one remains a 1 and everything else becomes a 0, as you can see quickly by going over these two representations. And then math.log basically gives you integer value for the position. And then, so this is some sort of a ceiling function which helps you get the actual thing. So you can try running this function for a variety of inputs and you will notice a pattern. And every time this function gets you the rightmost bit for any input number. So this is going to be very useful to us very soon. And in case you want to get the rightmost unset bit, which is the rightmost 0 for some reason, let's say, then you can simply negate the value of n and then pass it to the above rightmost set bit function. So that's it. So this flips the bits in each of the position of n. And then if you apply the above function, you just have the rightmost unset bit. That's all. And the last API that we have defined is the set bit function. So you have any input n and you specify your position. And in the bit representation of that n, this at the given position, the bit is set to 1. So this basically left shifts the bit 1 the position number of times, and then it does an OR so that the corresponding position is set to 1. That's it. So these are our helper functions which deal with bit manipulation. And we have a couple of others. So in the earlier demos, Shomi and Shrutiboy shared some hashing APIs, which were very useful. So Shomi, for example, used the inbuilt library for mapping strings to for hashing strings, and Shrutiboy also had a masking-based approach. So this is yet another technique that we can use to hash integers to our specification. So you have this input L, which is the maximum size of the bit representation. Also, remember that L specifies the number of locations or number of buckets. So where the inputs can be mapped to, because 2 to the power L is the number of target positions for the hash function. So given the L, and we have two values for our purposes. These are integer values, A and B, and we have our input data, which is also an integer. So we just multiply the input integer with A and then add B, and then we take modulo of 2 to the power L. So 2 to the power L, basically modulo 2 to the power L maps this input data to some value between 0 to 2 to the power L minus 1, which is what you want the hash function to do. So this is a variation of multiplicative hashing. And one important thing to keep in mind for this is that since the modulo integer, the integer that you are doing modulo with is even, and it's a power of 2 to the power L, you should ensure that here it's not M and N, it's A comma B. So here you should ensure that A and B are odd. But there is some theory which tells why that is necessary. Basically, you want the value that you generate here, the multiplicative part, to be co-prime with the one that you take modulo with. So this basically ensures that whatever hashing occurs for the input element, the hashing target is uniform. So basically the distribution of the elements which occur in the stream, the hashed value should be uniformly distributed. There should not be any hidden pattern or something. So we have this sort of a hash function. And now we have, of course, since it's a input stream application, you have this random stream generator. So for that, the way I have done it is you just specify a number, which is the number of distinct elements that can occur in the stream. And given this number, the list range of num basically creates a list from 0 to n minus 1. So it's a list of possible values that can occur in the stream. And random.choice basically randomly picks out one of those elements from the created list. So basically, every time you call this random generator function, it will randomly pick out one of the one of the elements from the allowable list of inputs. So this is our random stream generator, and we have one another helper API called the ground truth distinct count, which, as we discussed earlier, is basically you use a set data structure to take the list of the input stream and then count the size of the set which gives you the number of distinct elements. So ground truth distinct count gives you the accurate estimate of the distinct elements, and FM sketch will give you an approximate estimate of the number of distinct elements. So this set seed function is basically like Shrutima, I think discussed earlier, random.seed. To ensure reproducibility, you set a seed and then all the random functions can be made reproducible. So this is, you can change the values of the seed and see how it impacts the algorithm. So like in the earlier discussion as well, we have a number of hash functions. So we from the lectures, you remember that we usually deal with a family of hash functions, and each of the hash functions takes in input any of the input stream elements and maps them to one of the 2 to the power L possibilities. And so you have in this demo 10 different hash functions. So we will try to hash the input elements separately using any of those 10, and we'll see what happens with all of them, across all of them. So let us first discuss this function, which is the exact algorithm that has been discussed in the lecture. So we first specify a family of hash functions. So since we already know the number of hash functions, which is 10, and remember that, let me scroll up a bit. Each of our hash functions is defined by these 2 values of a comma b. L is common for this entire setup. We really didn't need to pass L, in fact, here. We just need it for the modulo operation. So L does not change, but the value of a and b dictates the hash function. So for generating the hash family here, what we are doing is we are just specifying a list of a and b values. And as we discussed earlier, we are ensuring that these are all odd numbers. So one interesting experiment that you can do is you can delete this 2n+1 thing, and you can just have a random function, which allows for even numbers to be specified here, and you can see how the performance is impacted. And I can tell you now that the performance will degrade. So anyway, so we have a list of hash functions, which is our hash family. The length of the hash family is 10, and each of them is specified by a and a b pair. So for each of the a comma b in the hash family, we do the entire FM sketch procedure one by one. So if you remember, we had the z variable from the lectures. Just to recap, you can see it here. You have a z being set to 0. So that's all we do. And then after setting z to 0, for each of the input data in the given input stream, we first get the hash code, which is the random 64 length bit representation. So for that for that member of the hash family given by this a comma b, and for the given input, we generate the hash code. And then we use our helper function, the get rightmost set bit function. And then we get the position of the rightmost set bit. And then again, as discussed before, if the position is greater than the value of the current value of z, then we update z. Otherwise, z remains what it is. So for this for this member of the hash family, we do this procedure. We get an estimate of z after looking at the input data only once. So you can see that there is only one single pass over the input data. We look at each of the input data only once, and then we get an estimate of z. And the final estimate for that hash function is given as described in the slides by 2 to the power z plus 1 by 2. So for each member of the hash family, we have a separate estimate, and that is populated in this estimates list. So we have 10 different estimates based on 10 different hash functions. And now, if you remember from the lectures, one of the ways to reduce the variability across the choice of hash functions is to take the median across these estimates. So the statistics package has this median API, which computes the median of this given list of values, and that's what we return. So this is the FM algorithm as has been discussed in the lectures. So how to now to trigger this API and see how well it runs. So I am set, this is the running part of the algorithm. The setup is now done. So I am setting the seed here. The ground truth list and the estimate, this is the lecture API estimate. So this estimate list is going to be populated. Now we are going to try different values of n. So if you remember, n is the number of distinct elements in our universe. So n is the possible list of items that can be seen in the input stream. The input stream may have, of course, multiple occurrences of the same item, but the list of possible distinct items comes from this n. So we are going to try different values of n, and that is given by this range of values. So for each of these values in n, we are first going to initialize a random stream generator. So if you remember, the random stream generator takes as input the size of the list of possible values, which is given by this n, and then it will randomly pick one of the values from 0 to n minus 1. So given this stream generator, now another, if you remember at the very start, so let me just scroll up. At the very start of this demo, we had specified the stream length, which was 2000 for our purposes. You can, of course, change it and try for different values. So after having initialized this random stream generator, we create an input stream of length m, or 2000 length input. And our next call of the stream generator gives you yet another random choice of the inputs. And we have now the input stream. So the input stream has values from 1 to n, 0 to n minus 1. And then we will have a stream of length m. So now we are computing the ground truth using our brute force, basically set length based approach. And we are appending the estimate. So given the input stream, we are getting the ground truth estimate and appending the estimate here. As well as we are using the FM sketch algorithm as was discussed in the lecture. And then we are getting the estimate according to the lecture algorithm and we are appending it here. And let us plot and see what it looks like. So ignore this one for now. Let me scroll down a bit. Yeah. So here, as you can see, in this plot, the x-axis denotes the universe size. So the value of the capital N. And we were ranging from 0 to 1000 with a space of 5, basically. And then in the y-axis, we have the estimate of the distinct count. So therefore, you can see the blue line, which is in the legend mentioning the ground truth distinct count. It's tracking the number of actual distinct elements in the stream. And the red line is a noisy estimate of the distinct count. So there is the pleasing property here that with the increase in the actual distinct elements, number of distinct elements, our estimate also sort of increases. So it increases to a higher value given the actual ground truth. So what possible changes can you make here? One possible change is, of course, you can try doing a mean instead of the median here, and the plot sort of changes because of that. So that's an experiment that you can try. You can also change the number of hash functions. Instead of 10, you can try maybe 50, and that will reduce the noise which is caused by any individual hash function. So it provides a better estimate. You can try changing the values of the hash family, a comma b, whatever values are being specified here. You can change the size of L. You can change the size of the target hash function length. You can change the input stream size. 2000 can be much larger, and you can see what happens then. You can change the value of capital N. So your universe can also be much larger. So a bunch of different experiments can be done, and you can see how the estimate varies. So In case anybody or any one of you have searched Google and come across this Wikipedia page for the FM sketch, there is a slightly different, I have pasted the link here. There is a slightly different version of the algo which is mentioned there. So there also you describe this hash family similar to what we did before. And for every member of the hash family, you run an algorithm, you get the estimate, and you return a single statistic of the estimate. It's just the algorithm part here that's slightly different. So what's different about it? Let's just discuss quickly. So here also, given every input, you are getting the rightmost position of 1, like before. So that part is the same. For every input, you look at it only once and you get the position of the rightmost set bit. The difference is you have this vector of zeros. And once you have the position of the rightmost set bit, in this vector of zeros, you set that corresponding position to 1. So this, as the Wikipedia article says, this zeros vector is keeping track of which positions have seen the rightmost one till now. So every time you get a rightmost one position, you set the corresponding bit to 0. And then after you have looked at all the input ones, you go back to your zeros bit vector list and you get the position of the rightmost 0. So which is the rightmost position that has not been set to 1 till now? And the estimate is given by 2 to the power b. So out of curiosity, I implemented it. And this also gives a pretty decent estimate. So let's look at the plot for that. So here you can see the Wikipedia algorithm, which estimates the distinct count. And like before, you have the ground truth estimate. And you can see also that this is an increasing function. This is quite noisy. There is a EKJ-like figure happening here. But the estimate increases and in fact is a almost consistent upper bound on the actual distinct count. So this is also a slight variation and it seems to work interestingly. And you can again here also try those same sort of variations given this notebook. You can change the bit length, the hash family, etc., the string length and so on. So yeah. So this is the demo. You will be given access to the notebook. If anybody has any questions, please go ahead. So I'll wait a couple of minutes if anybody wants to ask. And otherwise, if you don't have questions, since it's already 8 o'clock, you can leave. Please feel free. Okay, so I won't hold you guys back too long. We can leave now. Just a couple of last comments. So we will be uploading a recording of this video online. Please feel free to ask any doubts in the Google discussion forum, and we will get back to you immediately with the solution. And also we will be sharing these 3 notebooks, and you can play around with them. And following that, if you have any more doubts regarding the notebooks, you can also ask us. Please feel free to reach out. So that's it for today. If anybody wants to say anything, or then otherwise you can leave. Thank you. Okay, I think the last student has left, so let's also go. Thanks, guys. Yeah.
Thanks. Bye.
Bye.